My name is Siva Raghupati. I've been with AWS for the past 7.5 years. For the first 2.5 years or so, I helped build a couple of services. Amazon DynamoDB, which is a NoSQL database service, and later on, Amazon RDS, which is a relational database service. For the past 5 years, plus, I've been working with customers around the world, including Amazon.com, to architect their big data solutions on AWS. I lead our big data solutions architecture team. I'm a practicing architect as well. So I'm delighted to be here. My objective is to share some of the truths that I have lived in terms of design principles that have stood the test of time for me at AWS. And so this is a repeat session. So I worked hard to incorporate some of the services that we announced as well into the slides. I haven't quite got everything in the slides, but I factored in Glue, AWS Glue, and Amazon Athena into it. We'll see how it compares with other stuff. So let's get started. So in terms of what to expect from the session, so I'm going to go through some of the big data challenges customers are having. And I'll go through the architectural principles, the 5 architectural principles that has stood the test of time for me. That's probably the most important slide in this entire talk, and that's the center of my presentation, and everything else is there to support that. And then we'll use those principles to sort of simplify the big data processing pipeline, if you will. I'll break big data processing into multiple stages: collect, store, process, and consume. And then in each stage, we'll explore what technologies to use, how, and more importantly, why. As a builder of some of the services, I have been intimately aware of what considerations that go into building some of these services. So I'm going to expose the question why. Typically in life, if you answer the why question, the rest of that is details. It kind of falls into place correctly. So I'm going to touch on some of that. And I'm going to derive a reference architecture. It's going to be pretty colorful. You may or may not like the color, but we'll see. But then I'll also paint some of the design patterns, like real-time processing, batch interactive analytics, and we'll also touch on this data lake. Data lake seems to be the answer no matter what the question is for customers. We'll figure out what that is. We'll try to figure out. Nobody knows what this is. That's the truth. So one thing that I'm not going to cover in this presentation is really, there's no code. I believe you should get the architecture right before writing code. Also, I have a lot of slides. I'm going to run right into the top of the hour. So I'm going to stand outside and take some questions. I'm also give you my email as well, sivar@amazon.com. So if you have any questions that I cannot answer here, but you'd rather answer me privately, please drop me a note. And with that, the volume, velocity, and variety of big data is ever increasing. From an architect's perspective, what this means to me is probably about 5 years ago, people came to us and said, oh, I need to do 200,000 requests per second. Can you help me build end-to-end architecture that'll actually do these kinds of requests? That was, thankfully DynamoDB was there, so we could actually scale that and put that in there. But nowadays, that number is around 4 million requests per second. This could be big companies or startups that have become wildly successful that come to us and say, can you please help me build a system that can handle 4 million requests per second? That's a lot of requests per second. And then in terms of other data types, it could be files. For example, some of the large customers are sending in 150 terabytes of data per day. Again, 150 terabytes of data per day. Typically, this lands in S3, for example. And also on the other front, IoT devices and platforms are starting to send about 500 to 600 billion events per day. And if you look at, these numbers look pretty big, but actually your numbers may not be as big. But if you look at even these big numbers, how many people are building these systems, how long it takes to build these systems, it turns out 1 or 2 developers built the system in a few weeks. Now, how do you build these massive systems, scalable systems in 2 weeks? It's something that we'll touch into. You need to get your architecture correct. You need to use the right services, et cetera. So that's sort of the picture that I sort of live through every week these days. So I just wanted to paint that picture for you. And in terms of the big data processing as an evolution, batch processing is moving into stream processing. And most customers are evolving their systems from batch processing to stream processing. What this means is, for example, if you have a fraud detection system, rather than saying, well, this fraud happened, this is the report of all the fraud that happened today, it'll be probably more useful to say, well, this looks like a fraudulent transaction. I'm going to sort of treat this separately. On the other hand, this other customer coming into the site for the first time seems like a pretty reasonable customer. I'm not going to take them through all this pain to buy my product. I'm going to give them a fast path, right? So how do you make such decisions? So you need to basically tie in machine learning into your pipeline to be able to do this. Both your batch processing pipeline in a way as well as real-time processing pipeline in a way. How do you think about architectures to incorporate machine learning into your pipeline as another aspect that I will try to address? So in terms of the cloud services evolution over the past 7.5 years for me, when I started at AWS, yes, we did have S3, we did have SQS, but we had virtual machines. EC2 instances was what we had primarily. A lot of the customers were starting to use EC2. Over the course of time, we've already built services such as RDS. Rather than, for example, getting an EC2 instance, getting EBS volumes, RDS is a relational database service. When you push the button, specify your requirements, it gives you a database server running. It could be various engines, for example, MySQL or Postgres, et cetera. And then rather than actually you getting these instances, stitching them together, running a RAID across various EBS volumes, we do that for you, hence the word managed services. And then when I started on the DynamoDB team, I wrote the first version of the spec, in fact. What we wanted to do was to provide a simple API that'll say, create a table for me, here is the key, and just the key, don't have to describe the attributes. And then, by the way, give me 100,000 writes per second and 1 million reads per second. And that's it. Under the covers, we go ahead and provision everything for you. When the table is ready, it says creating table. And then in a few moments, the table is ready. And you start actually doing puts and gets into the table. I think of that as sort of even serverless. People try to think Lambda serverless. To me, DynamoDB, Kinesis, in a way, SQS is also serverless. You're not worrying about the box, what size of box you need to get. You're simply trying to specify, what data types go in are your requirements, and we do the rest for you. So actually building these serverless architectures into your, end-to-end pipelines is going to be fairly important. Now, how do you do that? And we'll touch on some of that. So luckily, there's a plethora of tools. On the left side, there's the open source ecosystem churning all kinds of amazing tools. If you ever been to a Strata, the Hadoop conference, Spark is the answer, no matter what the question is. So there's a lot of laughter in the room, so that should be right. So, and apparently this little squirrel at the very end, you don't know what the pink squirrel? Anybody know what that is? Flink. Apache Flink, right. It's going to challenge, the dominance of Spark, if you will. So as an architect, that leaves me in a little bit of a quandary. Now, should I use Spark, or should I bet on, the little squirrel there, Flink? So I think building systems in a way that obsolescence is going to happen, and how do you factor that system for obsolescence is a key thing as well there. On the right side, obviously, you have AWS services, starting from S3 through SQS onto Lambda, and today, Athena. So how do you basically factor this in? You probably didn't know yesterday or 2 days ago that Athena was going to be announced. Now, how do you factor in Athena into your pipeline? If you build your pipeline properly, you should be able to simply plug in, just as I did in my slides, which I'll show you in a little bit, right? So I think how do you build systems for future technologies that will be in play 6 months or 18 months from now is a key aspect that you need to think about as well. Now, in essence, what customers are asking us is there a reference architecture? What are some of the design patterns? What technology should I use? And how and why, right? So I think we're going to address the why and then see how the other pieces fall into play. So I talked about architectural principles. These 5 that I'll discuss now has stood the test of time for me at AWS. The first is you should be building decoupled systems. And I think I want to use a practical analogy, a car. I'm a mechanical engineer by training in my first life, and then a computer science person in the second life. A car is a beautifully decoupled system. So you have the engine, the gasoline engine, let's take, for example, that's running at a specific speed. The gasoline engines tend to run well at a constant speed. They don't like ups and downs. Whereas in real life, your road has ups and downs and various speeds. You can't take the corner at the same speed as you've been driving in a straight line. So there's this beautiful thing called a gearbox with the clutch. If you're familiar with the clutch, maybe some people who haven't driven manual are not familiar with the clutch. This thing nicely decouples both tiers, the engine as well as the wheels. In a way, in a processing scenario, what happens is you have two processing layers, and the storage really acts as this gearbox or a clutch that nicely decouples both of those. As long as you lay out your architecture in a way this is nicely decoupled, the downstream system can pump data at any rate that it wants, and the upstream system can pick up the data at any rate that it wants. And the middle tier, actually, the storage tier, nicely decouples this. So this way, actually, nothing blows up. Everything works at its own speed. You're shaping and dicing the data at its own speed. So I think using the right technology and the right decoupling really helps. Towards the end, I'm going to lay out 3 decoupled architectural patterns. One is I call as the data bus. The second one is pub/sub, which has been pretty prevalent with the advent of Kinesis and Kafka. And then the third one is what I'm calling as materialized views. So those are the mechanisms that will allow you to decouple these systems. And second thing, using the right tool for the job. One size does not fit all. Using the right tool for the job is paramount at AWS. When we build services at AWS, we typically build them to do a few functions extremely well, and we price them for that as well. So what happens is if you tend to use, in some cases, you could use 2 services for the same function, and in many cases, one service is going to be costing you much more than the other. So guess what? Which is the right service to pick? The most expensive service, right? No. the lesser expensive service. We'll go through an example. There's going to be a quiz at the very end, so you got to stay awake a little bit. So I hope you got some coffee. I did before I came here. So I think we're going to look at one of the key things to finding the right tool is also understanding your access patterns and also your latency, your throughput requirements, et cetera. So you need to understand what your application requirements are and sort of map that to the various services. What I'm going to do in the course of the presentation is lay out for various services what are the defining attributes that I found pretty helpful when helping customers. So it's going to be a pretty dense slide. I'm not going to go through everything, but I'm going to lay out some of the key aspects. So these slides will be available at the end of the presentation, probably in 2 days or a week, both SlideShare as well as YouTube. Hopefully, so you should be able to find the content there as well. So you can relax and take some notes or just listen. And third, leveraging AWS Managed Services is key. Rather than actually building systems, there are customers who tell us, I know how to run a specific database very well, whether it be Cassandra or Mongo. I'm picking 2 examples. But I've done that for a long time. In a way, can you please take this away from me? I want to use the managed services instead. And then they try to use Dynamo instead, right? Not that they don't know how to do this. They do this well at scale. But it comes to a point where they have limited resources, and they want to focus those resources for building tools and technologies that are very relevant for customers. They don't want to actually spend time actually installing software, upgrading software, maintaining software, et cetera, even though they know how to do this fairly well. And using AWS Managed Services is the key to the agility that I talked about. How does 1 or 2 developers, how do people build such massive systems in a short time? Clearly, using managed services, pushes a lot of the heavy lifting to AWS, so you can focus on your application scenarios. And then it basically gives you low admin or no admin in many cases, and also along with the various abilities, availability, reliability, et cetera. So the fourth pattern that is a principle that's super important is using log-centric design patterns. Maybe a better way of saying that is don't delete anything. And especially the logs. Transaction log, if you're a database person, transaction logs have been around for a long time. Typically, the way people back up databases is that they take a snapshot of the database, or they back up transaction logs. The logs are basically what are the changes that happened in a specific data table, for example, et cetera. You can always recover the state of the database by actually applying the logs forward. It's almost like your checking account or the savings account. You don't need to know what the balance is. Let's assume your database died. What do you know? How do you know what your balances are? If you had all those change, all the money you deposited and withdrew, you can clearly reconstruct the state. Similarly, when you have all these logs, you can actually have various views of these logs painted. For example, if there's a stream of data coming in, you may want to do actually a search on top of that, or you may want to actually put that in some other, a search engine or a relational database or a NoSQL database or various views or a graph view. Having the log and then creating various materialized views allows you to actually have a single source of truth, yet actually render this or view this in various formats. That's paramount. Again, that has stood the test of time for me at AWS. So the idea of immutable logs and materialized views is super important. Last but not the least, be cost conscious. Big data should not be equals to big cost. Typically, something is wrong. In many of my design reviews, which typically last about an hour, I park at 20-minute or 30-minute time and say, let's just figure out what is the cost of this solution. Usually 1 or 2 things come out of that. Either the customer says, all thumbs up, my God, this is $50, I love this, right? Or something like that. Or in other cases, they say, oh, this breaks the bank. What's going on here? The problem is either I haven't used the right system or right service, or in some cases, people tend to imagine things. They want to be wildly successful. That's all good. But if you're building a system 200 times more than what you really want, sometimes, first of all, you can't afford to build a system. Second, if you build a system, probably you're building for the wrong requirements. Both are essentially wrong. So being able to actually think about cost when you design plays an important role in picking the right tool for the job. So this is, I guess, the most important slide. The rest of them are details. We'll go through it a little bit faster. I spent a bit of time here just to focus on this one. And now let's simplify. With those principles, let's simplify big data processing. The more and more big data systems I help build, the more and more they look like this big pipeline, with the data going in from one side and answers coming out from the other side. And typically, there's multiple stages. Typical stages are collect, store, process, or analyze, I'm going to interchangeably call that, and consume. And what also happens is the store process repeats itself multiple times to shape the data in a form that's amenable for downstream access. So if you want the answers in a few milliseconds, obviously you need to have a NoSQL database or something that's already pre-indexed that renders that pretty fast. You can't go back into your data lake and start assembling all this stuff together because your time window has passed. If I need to serve an ad in 100 milliseconds, you just have probably about 3 or 4 milliseconds on the database tier to actually tell you, whether I should actually serve this ad or not. So I think it's pretty important to basically shape the data in a form that you will access it. And then what goes in there really is determined by, like I said, time to answer or latency, and your throughput, which comprises of the number of requests and the payload size, and also cost. So this, depending upon your domain problem, the length or the number of things that goes in there basically has a few constraints. Typically, those are the three top constraints. So now let's look at the type of data that we're dealing with. Typically, you're either dealing with transactions. Those could be, in-memory these days. In-memory databases are getting more popular. It could be your classic NoSQL databases or in-memory databases. And files. Files could be in the form of search documents that your Logstash sends it to your to Elasticsearch server, or it could be log files. For example, either CloudTrail logs or CloudWatch logs, or Flume, Apache Flume, or Log4j. All these subsystems are creating logs, and those logs typically end up in a log storage. And then either it used to be HDFS, it's quickly becoming S3 for all the AWS use cases. We'll delve into the details. And then also messaging, and more importantly, more recently, streams are the 2 different data types that are getting fairly popular. And before we get into kind of picking the right store for this, oftentimes when I think about solving a data problem, I think about the temperature of the data. What is the temperature of the data I'm dealing with? If I'm dealing with hot data, imagine data in memory, your various caches, and or data on SSDs, which is synonymous to warm data or cold data. When you're dealing with actually hot data, you're dealing with typically small payload moving really, really fast. You want very low latency in the order of milliseconds or microseconds. As you move towards the right, the time becomes milliseconds to seconds and seconds to hours. And then also the cost per gigabyte of storage actually tends to go up goes down from left to right. In other words, if you're putting it in memory, it's a lot more expensive than potentially putting it in Amazon Glacier, which is 4/10 after the price reduction, which is 4/10 of a penny per gigabyte per month. dramatically different cost points. It could be 2-digit dollars for the memory if you're putting this in memory versus few cents or fractions of cents per gigabyte per month. So having this notion of what is the temperature of the data I'm dealing with, it typically helps me think better or more clearly, which I'll explain how. Now we looked at the various data types, and typically records, both in memory as well as on disk records, go in either caches or SQL and NoSQL. And then search documents go into search stores, and files go into file stores, and then the messages typically went into message queues. And more importantly, the streaming data now that is coming from various platforms, IoT platforms, and devices typically goes into some kind of a streaming data store. Now let's look at what are the message and stream data stores. Now we're going to slice and dice each layer and compare and contrast various pieces in each one of those. Like, for example, Amazon SQS is a fully managed service for putting your queuing data, for putting your message queues. I mean, these messages could be something that you transfer between multiple applications, or this could be a buffering stage for downstream consumption. We'll contrast that with stream storage in a moment. And then Apache Kafka has been super popular for putting streaming data. For example, Netflix uses Kafka large Kafka clusters that they actually stitch on top of EC2 instances for managing all their events within the company. And then it works fairly well. The equivalent fully managed service is Amazon Kinesis Streams. It's a fully managed Kinesis stream. So in the case of Kafka, you need to basically install the software, get EC2 machines, get the right disks, install all the software, and manage the cluster yourself. Whereas in the case of Kinesis, you will simply say, create me a Kinesis stream, and then I need this much amount of throughput, single shard. Within the stream, there's multiple shards. Each shard is 1 megabyte per second ingest and 2 megabytes per second egress. And then you would simply basically provision the right stream, and you can scale that up and down automatically if you like by writing your own little application on top of that, for doing that. That's Amazon Kinesis service, streams. We also introduced Amazon Kinesis Firehose. For example, when we introduced Amazon Kinesis, the top thing the customers did were they actually stuck all the data in Amazon Kinesis and eventually took it to S3. We figured we'll build that for them. Then Amazon Kinesis Firehose was born. Firehose, simply if you write to a Firehose, you don't even have to specify the number of shards, et cetera. You write to the Firehose, you create a Firehose, and you write to the Firehose. And then it automatically bucketizes your data. It also compresses your data. You can compress the data with your own keys or KMS, key management service managed keys. And it automatically sticks them in an S3 endpoint that you like. A lot of customers love that because then they can run things like Athena to run queries on top of that. All of a sudden, all your streaming data magically is available for querying with Athena. That's an amazing scenario that this thing allows you to do. And that's an example of the Firehose. Also, Amazon DynamoDB streams. I think Werner touched in his talk this morning. Many people don't consider, a few years ago, I think about a couple of years ago, we introduced DynamoDB streams. Think of that as a transaction log of all the changes that happen. If you create a table, if you start putting data and updating data into it, you can also specify in my update stream, give me only the changes that happen. If you change your key for a specific customer, Joe, you switch to Flodos from A to B, you can get the prior image A and then the after image B as well. So it allows you to build very rich class of applications, such as you can index all your data that you put in DynamoDB by actually having a Lambda function take that and put that in Elasticsearch, for example. So that's a beautiful way of nicely decoupling this and then having your search index on top of your NoSQL database, for example. And so why stream storage? It allows you to, it gives you like three main things in terms of decoupling. It decouples producers from consumers. It also, by providing a persistent buffer, essentially if you have producers 1, 2, 3, et cetera, those could be devices. Rather than holding this hot potato of data that got generated, usually these little devices don't have much memory or capability. It'll be nice to hand this off to some other layer that'll be nicely persisted. That happens to be, you can put that in stream storage such as DynamoDB stream or Kinesis stream or Kafka topic. And And one of the other defining attributes of a stream storage mechanism is it preserves client ordering. In other words, if the producer sends packets 1, 2, 3, and 4 in that order, it ensures that a consuming layer consumes this data in the same order it was produced. For example, a lot of times at Amazon.com, we do what happens when people abandon the cart. Clickstream Analytics system captures all the stuff that happens in Amazon.com. When Amazon teams are actually analyzing why are so many people abandoning the cart at this specific point, maybe there's something wrong with the website, or maybe we're not presenting the right options. So what is the sequence of actions that a customer took as they walk through the site? This one, if you actually put the data in Kinesis or Kafka, that preserves that client ordering, so your downstream applications can do that. There's also another function called streaming. Before I get there, there's a parallel consumption paradigm that, as a pub-sub paradigm, this subsystems introduced, which means the same data, if you have two teams, in the case of Amazon.com, for example, we may have a fraud detection team, looking for if there's any fraud happening on that site. Or also, we do a lot of A/B testing. The A/B testing team has changed the website and is presenting different views to different customers. They're actually always running some tests on their site. They want to know how the clickstream progresses, right? Both the teams want to look at the same clickstream data. If you actually, rather than you asking the first team to build the pipeline for you and you consume that, these two teams can parallelly consume the data. So these subsystems allow you for parallel consumption, so the same stream is available for 2 or 3 or n number of teams, as long as you provision enough throughput that's available. Now, this is a huge deal for speeding up things within your teams. If you have 4 teams accessing the same data, they can all build their products and release at their own timeline rather than depending upon the first team to do it for them. And that's an indirect benefit, just want to highlight as well. And then last but not the least, what we call streaming MapReduce. For example, MapReduce, if the red producer designates all the packets that it sends as red, then the idea of doing a MapReduce is really finding out, give me the top n, what is the top value. Let's say if this is a temperature measuring device, what is the top temperature that you've seen, or what is the maximum temperature you have seen? That is essentially MapReduce. By just specifying key equals red, the mapping functions automatically happens within the stream storage. In other words, the red packet is ensured to go to a specific partition, and the downstream client framework, also like KCL client, Kinesis client library, also allows you to tie a single thread to that one stream in that case, that allows you to do computations such as min, max, average. So that automatically is enabled if you specify the key. One downside of specifying the key is because you're constrained by the maximum throughput of a single partition or a shard. So in the case of Kinesis, it'll be 1 megabyte per second. If you ever think that the producer 1 is going to send more than 1 megabyte a second, then you can't actually use the streaming MapReduce. So it's not for everyone, but for some cases, the streaming MapReduce functionality can be very well used. And now, what about SQS? This is a top question that comes, as an architect for me. SQS also decouples producers and consumers, provides a persistent buffers, allows you to collect multiple streams, but it doesn't give you client ordering. It doesn't give you streaming MapReduce functionality, and there's no parallel consumption possible. Even though there are parallel clients that can consume the data, if one client reads the data, that's not available for the other client to process. You cannot have actually 2 teams consuming the same input. As soon as the first team consumes that, it's not available for the second team. Now, as I drew the slide, I had to change this slide a little bit. Now, we also introduced a couple of weeks ago FIFO queues, right? When the FIFO queues now preserve client ordering. Now, what's the difference between, so I think the second picture there preserves client ordering. In fact, it does even deduping, if you will. For a moment, we'll compare and contrast that with the other queues in the next slide. Every exception has a special case, right? I said no parallel consumption. You can also enable parallel consumption by actually putting your data in SNS, creating a topic, and then have multiple queues subscribed to that. So you can pretty much derive the same thing that I said before. You can have the same data being sent to multiple queues by SNS. Some customers use that pattern. It works fairly well. And now, here's the thick slide with a lot of details. Which stream storage subsystem am I supposed to use? Customers tell us, please don't give me a menu. pick one for me. I'm sick and tired of seeing these comparisons, right? Now, we'll get to that in a moment. As a designer, first I want to show you the menu and all the parameters that are pretty much relevant. We'll go through the parameters. You'll find that interesting. Is it a managed service or not? Is there a guaranteed ordering or not? Is it delivered once, or is there deduping possible? Suppose if you're building a billing system, we don't want to double bill you. If you stuck your data in Kinesis and you didn't factor in for deduping, once in a while, the client may actually send you read the same data twice. In other words, if you faithfully build your customer, some customer is not going to be happy because they got double billed. So you need to somehow factor in deduping into this. Certain services allow you to do that. If you stick your data into Kinesis DynamoDB streams, for example, and you can actually designate if there's a key that you can dedupe on, you can come up with a semantic like the first writer wins or the last writer wins. So in the first writer wins scenario, you're basically saying, I already wrote to this, don't write the second packet, and you can avoid that, right? And also the other piece is also availability. If you're running Kinesis or if you're running Kafka, for example, you need to factor this in a way such that the Kafka is installed on multiple data centers or availability zones. For all the managed services, we do that automatically for you. In the case of Kafka, it's configurable. If you need multi-data center availability, you need to configure that. And just to kind of give you a set menu, if you have stream processing, if first in, first out is really available, if it's important for you, the best place to start would be Amazon Kinesis Streams. It turns out to be the lowest cost option. The best way to test this out is, for example, in the pricing examples, for every service, we give you this little pricing example at the one. In many scenarios, you can take actually the same pricing example and run through various services and cost out how much that's going to cost. When I actually took the pricing example for Kinesis, like 100 requests per second, 35K payload, and then ran it across all the services, Kinesis bill was $52 or something like that. Whereas if I did the same thing in SQS, before the price reduction, it was around $300+ or so. If I actually did this in DynamoDB streams and kept all the data, all the 10 terabytes of data will get collected if you write at the rate of 100 requests per second, but 24 hours a day, 35K per thing. Is 10 terabytes of data itself will cost you on just the storage alone $2,500. So unless if you use DynamoDB for deduping, what that tells me is I need to, if all the deduping functionality is what I'm using for Dynamo and then the stream functionality, I should quickly persist that in S3 and then delete all the old data, then you will not spend that $2,500 in Dynamo. So essentially, the summary is, if you're simply doing streaming data, I would say start with Kinesis streams. Likely you will not go wrong, unless something doesn't work there. You have other options there as well. Similarly, SQS, for example, has 14 days of data retention. In some cases, people don't care. They need just a buffering solution. They don't want to provision anything or manage any provisioning. SQS works fairly well as a nicely decoupling mechanism for messaging or streaming data as well. So I'll leave that for your further reference. The new Kinesis FIFO queues have a limitation of 300 transactions per second per queue. That's a hard limit. We're working on actually making that bigger, is what the team tells me. So, but nevertheless, I think those are the things that you need to be aware of. I thought I will just basically leave this for your future reference. Now, what about file storage? If you're talking about, the best place to put your data for files is Amazon S3. S3 is quickly becoming the HDFS for big data on AWS because it is natively supported by all the data, big data frameworks such as Spark, Hive, Presto, et cetera. And then, Impala did not have the support. They've actually put in the support as well for S3, I believe. And then the beautiful aspect of S3 is that it allows you to decouple compute from storage. So in other words, you don't have to run this Hadoop cluster keeping the storage. You can turn off your Hadoop cluster if you're not doing any processing. Your data lives in S3 with 11 nines durability and 4 nines availability. And you can also compress the data, and you can use your own key for encrypting the data, or you can let us manage the keys for you. And it also has tiering options. You can have S3 infrequent access. If you basically set a policy, it will automatically move the data between the tiers. We also announced some features to actually guide you as to how you should be moving this data rapidly into infrequent access or Glacier, et cetera. So suffice to say, there needs to be a good reason not to put data in S3. starting with S3 is almost always the right answer for your file data on AWS. And it also allows you to use spot instances. So since you don't have to have this cluster running, if we pull off the spot instance from you because the spot market went up, you can simply request for more instance and keep continuing processing, or you can come back and process that later when the spot price actually dips down again. So nicely decoupled. The key point is S3 allows you to decouple storage from compute. And sometimes you need a little more speed. HDFS is slightly faster than S3 on a if you don't actually parallelize it, for example. So in many cases, customers still use HDFS as sort of an intermediate store between multiple processing stages. And then you do all the processing and then eventually store the data in S3 and then shut down the cluster if you don't need it. And then, as I said before, you can also set a policy in S3 saying, let's assume you all the less frequently used data after 6 months, you don't tend to use your data set that often, then you can set a policy saying all these prefixes, go ahead and move them to S3 infrequent access. Or you can move them to Glacier infrequent access. With the price reduction, S3 is about 2.3 cents per gigabyte per month. S3 infrequent access, I believe, is 1.5 cents per gigabyte per month. And then also the S3, the Glacier is, I think, 4/10 per penny per gigabyte per month, right? So you get immense. I said don't delete anything. Now you need to aggressively implement your policies to move your data between multiple tiers so that you're paying the right cost for the gold, which is the data that you have. And then what about in-memory databases? Let me go back a little bit. What about in-memory databases and the classic database and search? In terms of this is the anti-pattern. In other words, don't do this. So I love Swiss Army knives. Those are beautiful and nice gifts. And that picture I'm passionate about. I got this from the Amazon site. And that thing cost about $800 a few years ago. I don't know if we sell them anymore. It was called the big Swiss Army knife. If you have a big screw, one way of actually dealing with that is to buy a screwdriver. And the other way is to actually get a big Swiss Army knife. The difference is a screwdriver may cost you about $10 or whatever it is, but then this one is $800 when I last looked at it. So the point is relational databases have been around for 30 plus years. They still work very well. They have a very valuable function, but it's not a good reason to use relational databases for everything. Most of the ad serving scenarios, people serve ads at a million requests per second. If you need to use a relational database, first, you don't probably have a relational database. I don't know about anything that'll serve a million requests per second. Number two, if in DynamoDB, you can just say, give me a million requests per second and then 100,000 writes per second and pay for exactly what you use. And that's not possible. You need to scale for one dimension, and you need to get all these other things for free that you'll never use, but still pay for it, right? So not a good idea. Instead, thinking of your data tier as comprising of multiple things such as in-memory, NoSQL, SQL, and search is a pretty important paradigm. Now, it's easy to say this, but now where do you put your data really? That's why we have all these 4 services. For example, Elastic Cache is a fully managed service for running either Redis or Memcached. We also recently introduced Redis clusters, super important ask from a lot of our customers. Worth taking a look at it. Again, as I mentioned, DynamoDB is a fully managed NoSQL database service. RDS is a relational database service, which is fully managed. We have various engines, Postgres, MySQL, SQL Server, Oracle, MariaDB, et cetera. And we also have Amazon RDS for Aurora, which is we've completely redesigned the storage subsystem as well as the logging subsystem to scale out their database till it has a MySQL interface. We also recently introduced RDS Aurora for Postgres. So Aurora is a 64, the maximum size is 64 terabytes. If you have 16 read replicas, you can do in the order of about, more than 1 million reads per second. And then I'm almost about 100,000 writes per second in using a relational system, RDS family of services. And then Amazon Elasticsearch service is a fully managed service for running your Elasticsearch. Elasticsearch is super popular. A lot of our customers love the fact that we manage the clusters on their behalf. And now, which data store should I use? Well, it depends upon your data structure, access pattern, your data characteristics, hot, warm, or cold, and the cost. This access pattern modeling, I've done a lot of DynamoDB design reviews. The essence of the review is really finding out what the question goes like this: can you please tell me, what are the final queries you're going to run with this database? Then you start designing your data structures, your key patterns for the end access that is required. When somebody comes to use a NoSQL database, they need speed and scale, which is usually the paramount for them. That's why they're using NoSQL anyway. And then starting with the end in mind makes a lot of sense. So what I've learned, doing this data business for 25 plus years is that storing the data in the most efficient form it is accessed is usually the right answer for many scenarios. The fancy name for that is materialized views. So now, what structure, if you have put get value, if you have simply doing puts and gets, using either a NoSQL or an in-memory database is usually the right answer. If you have a simple query pattern, like one-to-many parent-child relationships or many-to-many, and then usually a NoSQL works fairly well. If you have complex queries and transactions and joins, obviously the good old relational database works extremely well. And then if you have faceting, if you go to Amazon.com, on the left side, we give you, when you search for something, we facet that by, is this Prime enabled? Is this by seller A, B, or C? All that faceting is very well done by, search engines. They are super optimized for doing faceting and searching. There's no point in running SQL queries to do faceting and searching. The best thing to do is to actually use a search engine to do faceting, because faceting is a first-class data type. The indexes are primed for doing faceting. And similarly, if you have a fixed schema using SQL or NoSQL makes sense. Schema-free, which is JSON, NoSQL or search works fairly well, and key value, memory or NoSQL works fairly well. When somebody reviewed this slide, they said this is the ugliest slide that they have done. This is like telling your baby is ugly. I thought really very hard to make this slide, and so, well, being a little bit upset, I still, it's my baby, so I want to keep the slide, right? So the idea here is that I was trying to convey my idea of like a multi-dimensional thing. The structure of the data is high and low. On the left side, I have an axis, low data structure. In S3, it's a simple key value. It's a low data structure. If you go down, it's a higher structure. You put complex structures in like search engines. On the bottom, you have all the parameters that I use for hot and warm, request rate, cost per gigabyte, latency, data volume. The way I think about, imagine all the services, having been a builder as well, we tend to build a spectrum of services, right? Starting from in-memory, NoSQL, search, S3, et cetera. There's a bit of an overlap between these services. In some cases, when you're building a system, you could do this in either a SQL or a search in other places as well. So as a designer, that gives me an idea of, when I'm talking to customers, I'm always factoring in, where does this workload belong? Is this a hot data set? Is this structured or non-structured? So I'm basically going into this two-dimensional or n-dimensional space. And sort of, that's how I was able to paint my brain. Maybe it's ugly inside, but so now what I've done this is that actually painted that same hot, cold. I'm used specific services here, and I've actually given those various attributes, latency, typical data set storage size, request rate, et cetera. I'm not going to go through all of this for the sake of time, but I'm going to leave this here. The basic idea is if you want to basically have a millisecond level access, 1 millisecond or less, typically Elasticsearch would be a good place to start. Whereas if you look at the durability wise, for example, somebody asked me the other day in one of the EBCs here, briefing reviews, like I'm really getting confused. Should I put my data in Elasticsearch or DynamoDB? I told them if durability is super important for you, and this is the crown jewel of your company, I would pick a store that is bulletproof in terms of durability. For me, that's DynamoDB. And then you should simply maybe have a view or do your caching using your Elastic Cache, but you should actually stick your data into DynamoDB. And so, because if you look at this graph, it says durability should be low to moderate in the case of Elasticsearch. Durability is very high. That is the right answer for this scenario. This is an example. I want to move on to the next slide. Now, this is where the quiz comes in, right? So this is a question that some customers sent me. The person is trying to decide between Amazon S3 and DynamoDB. They're scoping for the new project. In terms of this is, if you boil this down, it turns out they're doing 300 writes per second, 2K payload, 1.5 terabytes of data they'll store per month. and then the number of objects stored is 777 million. Which data store should you use? How many think it's S3? A few hands here, 1, 2, 3, 4. S3, anybody? A few hands over there. I mean, the sad news is that one of this is the winner for now. Still S3? How many say DynamoDB? A few more hands. Anytime that there's a tie, there's this beautiful thing called a simple monthly calculator. It's not perfect. It's not perfect. In some cases, I had to run my own Python program to actually find out the cost. But it's a good start. If you plug in those numbers, it basically tells me $644 is the DynamoDB cost, whereas an S3 is going to be $3,932. People who said S3, unfortunately, you lost this one, right? It turns out that they were thinking right. They were thinking storage. It only costs $44 for storage if you use S3, but turns out that the put prices is $3,888. When I actually showed this slide to the S3 product manager, the person was pretty unhappy that I'm going to present this to 500 plus people and tell them don't use S3. So I did have to put a compensating scenario. So I changed the game. So I basically, even though the customer requirement was first, I came up with another requirement saying that the size of the payload is 32K. It turns out S3 is the winner in that scenario, because DynamoDB is very good for smaller data sets moving really, really fast. But when the payload becomes very large, DynamoDB can handle it too. 35K, it can go until 400K. But what happens is the price increases because, so that in this case, clearly what our pricing tells you is, go ahead and pick Dynamo S3 when the payload is fairly high, and DynamoDB when the payload is small, low. And usually that is the right answer if you're going through all the details. I'm going to leave it for thinking. This is just a small example. It's a real example, but the same example applies in many, many scenarios that you will go through, especially if there's a conflict of using potentially two services. So quickly going through process and analyze. You're dealing with either batch processing and interactive. In the case of batch processing, using MapReduce, Hive, or Pig is the right answer. In the case of interactive analytics, Amazon Redshift, Amazon Athena belongs there in the case of interactive analytics. And then, or you can run Amazon Elastic MapReduce with either Presto or Spark. And in the case of messaging, writing an SQS app, either in terms of Elastic Beanstalk could be a container for actually running your app, processing messages. That usually works out fairly well. In the case of stream processing, you have a lot of options. Starting with Kinesis Analytics is a fairly new service that we launched. And then it's serverless and so on. Or you could use Spark streaming, or you could use AWS Lambda, Strom, and Kinesis client library-based apps. In the case of machine learning, Spark ML is super popular. In conjunction with Spark ML, you can also use Amazon ML. We're also releasing a slew of services, machine learning managed services as well as other services as well. So we'll see how to tie that into the pipeline. So this is, again, a chart of which stream and the messaging store that you should use. And again, here I have given you multiple dimensions here. So if you look at, if you want serverless, there's two choices, Amazon Kinesis Analytics or AWS Lambda. And then if you look at, so basically, based on the kind of processing that you want to do, you can pick the right answer. So I would say, if you're doing, general purpose stream processing that needs to infinitely scale, clearly KCL, and if it's Kinesis, you're using Kinesis client library application or Spark streaming would work very, very well. If you're using Spark streaming, you should be aware that that runs in a single AZ if you're running this on top of EMR. So if you need multi-AZ or multi-data center availability, you need to be able to run another cluster when one data center goes down, and you need to have both clusters processing that and persist that data in a common store to be able to do that. So I think those are all the parameters that were super helpful. I'm not going to go through each and every detail, but this is for your reference. Similarly, what analysis tool should I use? We launched Amazon Athena. Amazon Athena is a fantastic tool for using ad hoc and interactive queries. Basically, you put your data in S3. You could use any of those data formats. It could be CSV, it could be TSV, it could be JSON, Parquet, or ORC. Parquet and ORC are columnar formats. Or it could be even an Apache weblog. So you can use the right Serde. When you create an external table, you'll say create external table with the specific Serde, serializer, deserializer, and then off you go running queries. We keep that metadata definition in the Athena catalog, and you can run queries and then materialize results. If you have a classic data warehouse workload, Amazon Redshift is the best place to put that data. And then if you have general purpose workload with a lot of iterations that you want to build in machine learning, you want to also combine real time with machine learning, Spark works fairly well. And for example, Netflix uses a 60 petabyte data warehouse that they built on top of Presto and EMR, right? Fantastic tool again for processing, for running interactive queries. So that's sort of how I think about these are all the specific attributes that were quite helpful in making decisions for me. So I've documented this for your future reference. And now, what about ETL, right? Obviously, you saw the Glue announcement. In combination with Glue, we have amazing partners in that space. Starting with Alteryx, Tunity, Informatica. These are all various names that a lot of ETL, amazing ETL vendors that we have. In addition, we also launched AWS Glue, which will also be super helpful for ETL. I'm not going to go into the details of this. I'm going to leave it at that for now and move on. On the consume tier, now we talked about storage and processing. We're going to go through consumption quickly. And then there's two classes of users, or perhaps more. The main classes are business users are going to go through some kind of a UI. It could be Tableau, or it could be QuickSight that Werner showed this morning, or it could be Looker or MicroStrategy, et cetera, actually slicing and dicing the data that you put in your data tier, such as RDS, or on Redshift, being able to materialize an answer. And most recently, notebooks are getting fairly popular. We have a number of articles in the AWS Big Data blog. This is a fantastic place for your reference. We keep launching multiple blogs per week. And then we have a number of blogs as to how do you run notebooks on top of Elastic EMR, for example. Notebooks are getting fairly popular as well, especially Jupyter and Zeppelin. And our studio for data scientists is key. There are a few talks actually in the big data track where people have gone through exactly how, I think it was FINRA had one talk on this one. Probably Netflix might have touched on this aspect as well. So there's amazing talks on how do you actually enable these two classes of users in the big data track. I'm going to leave that as a homework for you. Now, putting it all together, that's the fancy, colorful picture reference architecture that I came with. I'm going to show you a more fancy picture at the end. You got to hold on to this. OK, so design patterns, the three primitives I told you about. One is the decoupled data paths. It should look like something like this. Store process should repeat itself. That's the first way of decoupling. And the second way is using the pub/sub paradigm. Kinesis, put data in Kinesis, have multiple consumers consuming that. In this case, I've shown Amazon Kinesis connector library, as well as Lambda and Spark, processing the same input, parallelly deriving various outputs. That's the second way of decoupling those. And the materialized views, if you have a framework that can access from multiple data stores, in this case, Spark is materializing an answer that you put, an answer from the data that you put in S3 and DynamoDB and Kinesis, and rendering a picture. So the idea of materialization and decoupling that from storage makes a lot of sense in my mind. So this is, again, beautiful or ugly, depending upon how you see this. So what I'm trying to paint here is on the x-axis, I have various storage services, hot to warm to cold. And on the y-axis, I have various processing applications. The combination of a hot store and a fast processing technology lends itself to real-time processing. And the combination of a warm store and a fast processing technology lends itself to interactive query or analytics. And the combination of maybe hot or warm store, cold store with the batch processing, which is slower processing stack, allows you to do batch processing. Now, we're going to spend the next 7 minutes actually going through like 3 different architecture types. I'm going to draw it to the end, but I'll take questions at the end after. And so that's sort of this is a mental map that I have. It's been quite helpful for a number of customers. I mean, that's how I think about these various types of analytics. And so here is a classic stack for real-time analytics. Your streaming data goes into Amazon Kinesis. I'm going to use only managed services here for obvious reasons. And you can actually do in-stream ETL using Kinesis analytics on that. So basically, you can run your SQL queries and just say, from the incoming data stream, go ahead and only filter these one out or generate other output based on that. And you can stick that into another Kinesis stream or a Kinesis fire hose, right? In this case, I'm doing real-time analytics. I'm going to stick this back into another Kinesis stream. So once you have this in Kinesis stream, again, you can use all those applications that we went through. Now, we did a comparison of that as well. So this is not a big menu. In your case, you're going to probably pick one of this, right? Or perhaps two of this, right? Either you could do a KCL or AWS Lambda or Spark running on top of Elastic MapReduce to actually process the data, and you're going to store your application state in some kind of a storage subsystem. It could be SQL or NoSQL. It could be cache, such as Redis, or it could be Elasticsearch. And you're going to render a KPI using some kind of a drawing tool. It could be platform or some D3, some graphing library. And also you can in some cases people do fan out. In other words, they have an application, all it does is simply take the data that comes into Kinesis and puts that in another Kinesis stream. So if they have 20 teams processing that, you need more read throughput. Therefore, you need to fan out, so you can actually fan it out using that paradigm. The most important thing here is the log, the arrow that's going to the log. I always tell my customers, write one simple application that processes the data, doesn't change anything, and sticks it in S3. Keep it as simple as you can, and don't touch it. Because data is gold. It's best to keep a copy of the data untouched in some place that you can always go back to if something falls through. Super important. And in the case of interactive analytics, same kind of an idea. Your streaming data goes into Kinesis Firehose, and then the Firehose can automatically transport the data to Redshift or S3. And then what I've not shown here is Elasticsearch. And you can also, if you're doing real-time predictions, for example, you can also, the paradigm of tying machine learning into your thing is, for being machine learning experts, there's two aspects to it. Either you are the person building the models, or you're a user. If you're a user, it's like driving the car. You don't need to know how the car engine is assembled together, as long as you know how to drive a car. What I presented here is if you have interactive analytics, there are many services that we have announced now and will come up with, hopefully going forward, that all you need to do is to send the user and ask the question, is this fraud or not fraud? You'll get an answer back saying yes or no. And that's all you need to know for actually materializing the result. Now, how do you generate the model? How do you tune this? That's a separate thing. So when I draw a line here, real-time predictions, that's what I mean. The stack is passing the data and asking a question, yes or no. Similarly, batch. You can give a batch of users and say, can you please classify them into fraudulent or non-fraudulent users in your batch processing? And this system will come back and say, well, here's the location of all the thing that I did after a little while. Then you can tie that into your downstream system, right? Now for the famous thing, data lake. Well, I put a question mark there in my first slide, and somebody said, remove the question mark, and I removed that. But nevertheless, we're all trying to figure out how did you do log-centric processing? How do you do the single version of the truth? The best thing is to basically have a stream of data coming in, having the original stream in S3, and then materializing the view and serving the view to downstream application is the main paradigm there, right? And using all the principles that we learned of nicely decoupling systems along the way, like Werner pointed out, there's always going to be silos of data, But having a single point of truth in S3 in the most unprocessed format, and that is going to be the gold for your organization as long as you have that. And it's very hard to just use that to materialize every single answer. In many cases, you'll have to materialize this answer ahead of time when you're serving downstream requests fairly fast. What I've done here is simply combined the interactive and the batch, and then the real-time analytics. And I have nicely decoupled this with the storage subsystem there to serve the answers in the case for downstream applications. So that's the essence for me of a data lake. And essentially transactions, files, streams goes into your lake, and then you persist an original copy of that in S3, and then you transform that into using various downstream applications to render the views and downstream applications that you want to serve. I want to leave it at that. To summarize, you should be building decoupled systems, and nicely decoupled pipeline is fairly important. That lends you scale, that lends you the ability to replace a various subsystem as you move along. If you don't like your processing application, today we announced Athena. If you're doing, for example, all you're doing is running simple queries using Presto or something else, then you can simply use Athena instead of that. The basic assumption is as long as your data is in S3, you're good to go. So if you nicely decouple your system in S3, it should be tomorrow you should start using, actually testing with this new service that we launched. And using the right tool for the job is paramount. We went through, I showed you various examples of various attributes that you need to compare and contrast to pick the right tool. In many cases, it's not a menu. Quickly, you'll narrow down to 1 or 2 services. Then you can always break the tie with that or go with one. And AWS Managed Services is key. That gives you the speed or agility. And so you don't have to deal with managing the systems, et cetera. And using log-centric design patterns, don't delete anything. Keep a copy of the logs because you never know what questions or what machine learning models you may be building in the future. And data, as Werner pointed out this morning, is the biggest differentiator because every other company is going to be using the same applications and services. Your data is the gold. And then keeping that safe is paramount, and keeping that in low-cost services such as S3 and archiving that to Glacier is super important. And be cost-conscious. With that, I'm going to give you the most colorful picture that I've drawn so far. You may hate or like this, but what I also did is put some Lego blocks. If you basically plug in the Lego block, I'm going to take Kinesis fire hose. It has this color. Should I call this pink or should I call this violet? I'm going to call this violet. That's going in. It has a V in there. If you actually match that, the processing layer that can access that is Redshift, right? If you put in Kinesis, you can see another layer that actually Lego blocks into that. Amazon Redshift does that. Also, Kinesis Analytics can process that. So I tried to draw all kinds of lines, connecting them. Soon, I couldn't read my slide. So I went to a graphic designer and said, can you please somehow tell me how to abstract that? And she came up with this paradigm of these Lego blocks thing. It's back pretty well. So I'm pretty proud of that Lego blocks. With that, I thank you for your time. And I hope that was helpful. And really, really appreciate coming to the talk.